All right, so I want to show you how to calculate the equilibrium constant. And in this video, you should learn a few things. We're going to show you how to write a balanced chemical equation or an equilibrium equation. I'm going to show you how to write an equilibrium expression, so KEQ equals something, how to use an ICE table, and then how to calculate the equilibrium constant. So our question today, we have solid ammonium hydrogen sulfide. It decomposes forming ammonia and hydrogen sulfide, and both of those products are gases. We have 3.25 moles of the ammonium hydrogen sulfide placed in a sealed 2-litre container. The system then reaches equilibrium, at which point we have 0.298 moles of hydrogen sulfide, and the goal is calculate KEQ. So step one, we're going to use the first sentence in that question to come up with a balanced chemical equation. And the reactant, in this case, we have ammonium hydrogen sulfide, the formula given here. It decomposes, forming the products ammonia and hydrogen sulfide. So coming down, there is my solid ammonium hydrogen sulfide. It then changes into ammonia, a gas, and hydrogen sulfide, also a gas. I need to check this reaction is balanced. There's one nitrogen on this side and there's one nitrogen on this side. We have 4 plus 1, 5 hydrogens here, and on this side I have 3 plus 2 more is 5, so that's balanced. And then I've got 1 sulfur and 1 sulfur. So it's balanced, no need for coefficients. And the last thing, note I've used the equilibrium symbol because this is an equilibrium reaction. Step 2, we need to extract the data. We need to pull out the information that's going to help us solve this question, and all that happens to be in the second sentence. So we have 3.25 moles of ammonium hydrogen sulfide, and it's placed in a sealed 2-litre container. So initially, there's 3.25 moles of the ammonium hydrogen sulfide, and the volume of the vessel is 2 litres. The system then is allowed to reach equilibrium. So at this point, this ammonium hydrogen sulfide starts to decompose, forming our products. And at equilibrium, we end up with 0.298 moles of hydrogen sulfide. So moles of hydrogen sulfide at equilibrium is 0.298 moles. Step 3, it's time to write an equilibrium expression. So KQ equals the concentration of the products multiplied, divided then by the concentration of the reactants. So I have ammonia and hydrogen sulfide, and according to this reaction there's one of each. There's no coefficients here, so I just multiply them together. I would normally divide this by the concentration of the reactants, but as this is a solid, solids have no concentration, so I would treat that just as 1. So the equilibrium expression here is just the concentration of ammonia times the concentration of hydrogen sulfide. Next step, we need an ICE table. So ICE stands for I is initial, C is change, and E is equilibrium. And we create a column for each of the reactants and products. So in this case, my reactant is the ammonium hydrogen sulfide, and then it's going to change into my 2 products, which is ammonia and hydrogen sulfide. So initially, this value here, the initial number of moles of ammonium hydrogen sulfide, we know is 3.25 moles. We got that from the question. And when it was initially placed into the reaction container, there's no mention of anything else that was placed. So initially, the 2 other substances had no moles present. So next step, I want to try and work out how those things are changing, and each of them are going to change by X moles. They're going to change in stoichiometry ratios. So coming across the equation, it's in a ratio of 1 to 1 to 1. So it's 1x, 1x, and 1x. If there was a coefficient there, then it would be, say, 2x and 1x and 1x, whatever the coefficients happen to be. But because they're all ones, I'm just going to have x, x, and x. So the next thing I need to consider is the reaction is shifting towards the right. We are decomposing the ammonium hydrogen sulfide and forming those two products. So as a result, that is going to cause the amount of ammonium hydrogen sulfide to decrease. So I use a minus sign, and for the other ones, they're going to increase. So they're going to have a plus sign attached to them. So that's how you would assign changes. The next step is to determine the change, and we read down the ICE table. So 3.25 minus X equals the number of moles at equilibrium. And reading down this one, it's 0 plus X will equal X. And reading down this one, it's 0 plus X equals X. And I happen to know that that value is 0.298 because I was given that information in the question. So next step, I'm going to need to try and calculate KQ, but if you come across back to the expression, you can see that KQ equals the concentration of ammonia times the concentration of hydrogen sulfate. So the squared bracket there means concentration of. So I need to convert these moles values that I got in step 4 into concentrations, and I do that by taking moles and dividing by the volume. So the number of moles of hydrogen sulfide was 0.298, was there, and the volume, 2 litres, came from here. So that gives me 0.0149 moles per litre, and the number of moles of hydrogen sulfide is the same as the number of moles of ammonia, as you can see from here, X and X, they're both the same. So now I can substitute into my KQ equation. So number of moles of ammonia is 0.0149, and the number of moles of hydrogen sulfide is also 0.0419. Multiply them together gives me 0.0222, and if I convert to scientific notation, that gives me 2.22 by 10 to the minus 2, and I've elected to use 3 significant figures for my answer. Why? If I go back to my original question, this set of data had 3 significant figures. This one also had 3 significant figures, and so did this one. So my answer will have the same number of significant figures. All right, so we've done our calculation. Now maybe you'd like to have a turn. So this is exactly the same question, but I've changed 4 values. The values are all highlighted in red. So the number of moles of ammonium hydrogen sulfide has changed. The volume of the reaction container has changed. The number of moles at equilibrium of ammonia has also changed. So you should be able to substitute those values in and duplicate the question that I've just done, and if everything goes to plan, you will get the same answer that we got for the previous question. So as a final question, you might like to answer, why is KQ the same for each of these calculations? Thanks for listening, and hopefully this has helped.